So, good afternoon and welcome to this A2EP webinar on modelling, optimising and integrating and getting more from your heat pump. My name is Jared Leake and I'm the CEO for the Australian Alliance for Energy Productivity. And I'd like to commence this webinar by an acknowledgement of the traditional custodians of country throughout Australia and their connections to land, sea and community, and pay my respects to their elders past, present and into the future. For those that are new to A2EP, we are an industry association, non-for-profit, funded by these fabulous members right here, and they share our vision of improving energy productivity through Australia and helping with decarbonisation. So many thanks to this wonderful set of members. For this webinar today, we will be recording it and sending out this recording and the presentation slides early next week, so they'll go out to you if you've registered. And we're certainly hoping to have lots of questions from the audience today. So please feel free to type in the Q&A a question there, or upvote someone else's question that you like, or have a bit of a chat using the chat box there as well. But please, put those questions in, and I'm sure we've got time to look at those today. Joining me today from the A2EP team, we have Brendan Voss, our project manager and looking after research programs that we're doing. Brendan, hello and welcome. Brendan, this is our second out of 4 heat pump webinars this month. Last week we had Dr. Corden Appelgaus talking about high temperature heat pumps. Any takeaways for you from that one last week?
I think main takeaway for me was seeing some passion come through from Corden on wanting to see, some of the systems, I guess, be furthered or the efficiency be furthered. It was great to see someone leading the charge with actual factual-based research. So it was the enthusiasm he has really came through. So it was just great to listen to.
He really is the premier person there in globally understanding what's happening with developments of high temperature heat pumps, and this is I think 3 or 4 years in a row that we've had Corden on, and amazing to see the development over the last few years. It's really jam-packed with higher temperatures and more suppliers. So good one. Brendan, thanks very much for joining me. I'm looking forward to helping with the Q&A and chiming in with some questions for our presenters here today as well. So this is a fantastic lineup we have for you today. We've got Team Beca, who apparently well and truly ahead of the game with lots of knowledge on heat pumps and that GIDI funding in New Zealand absolutely coming in, and lots of experience and learnings coming out of that. And we're going to hear about what Beca has for knowledge in terms of optimising heat pumps and integrating with solar and what have you. So we're going to be hearing from Beca a little bit later. But to kick us off today, we have Doug Smith from Coolsheet. Doug is the CEO for Coolsheet and has quite a vast experience with solar PV after working for BP Solar, RES and Hanwha, but now moving into the world of integrated solar with solar PVT. Doug, I'll get you to share your screen, but while you're doing that, I'll say that interesting that we've been always been about energy use and energy demand, and almost like, look, energy supply, there's enough happening over in that area. But as there's more and more people are employing behind the meter solar, and as they need more flexible usage of their energy, that line's getting more blurred between supply and demand. But then once you look at integrating and looking at a PV thermal, that integration and that overlap has happened even more. And with the technology that Coolsheet has, it looks like we're going to see a lot more of this. Doug, over to you to take us through this technology.
Thanks, Jared, and thanks everyone for joining. I'm talking to you from Camarago land and the North Shore of Sydney, where we have a manufacturing facility. And I think over my left shoulder you can see one of our Coolsheets. Let me just check we are running. I have sitting in the wings the mastermind behind this. Tom Hoole is the founder and the CTO and the inventor of the Coolsheet. So if there's any prickly questions in the chat, then we can have them answered hopefully straight away. Coolsheet. What what problem are we trying to fix? Well, I think no surprise to most of you attending this webinar, traditional way of heating water is expensive, inefficient, and unsustainable. We've been passionate about creating an innovative solar thermal solution and manufacturing it here in Australia. And it does two things effectively. It's a preheat for water solution and offsetting fossil fuel use, and then cooling solar panels, which improves their efficiency. Just going to go through PV thermal, PVT, for those for whom it's new. Been around since about 2007, but it's picking up a pace now globally. And then the most common use cases we can see in Australia and New Zealand, and then just a couple of points on integrating with heat pumps and modelling considerations. So Coolsheet is a heat exchange panel. It's an aluminium heat exchange panel, and it sits on the back of a solar panel. It's using thermal conduction effectively to capture waste heat that builds up in the silicon and the glass and the metal of a solar panel. So quite simply, and it gives you two outputs. Input to the hot water. Economics don't make sense yet unless you're needing some hot water. And then the cooling of the solar panel, which is an excellent byproduct. We can make Coolsheets that go into an existing PV system, which is quite interesting, particularly if you've got a 1 megawatt, 500 kilowatt, even 100 kilowatt PV system on your own roof or a client's roof. And new build is, of course, a slightly more effective installation cost. The product fits entirely within the frame of the solar panel. We can make Coolsheets for a number of different sized modules. The Coolsheet's one of the lightest PV thermal panels on the market. The average panel size is about 8.5 kilos. Solar panel weighs about 23. Bigger ones are heavier, but that's the average size. What's quite neat with this solution, which is patented by Tom, is it's extremely low maintenance, almost zero maintenance. So it's been designed to fit and forget, sitting behind a solar panel for a long life, up to 25 years. And then we have a quick connect plumbing solution as well. So really, we're trying to minimize the number of contractors on the job, safety message, but also an efficiency and a cost message. And yeah, there's a number of other benefits to having as few contractors as possible. We'll get questions. How does it actually work? I think this is a useful graph. Interested in feedback. Of course, we all know solar panels convert sunlight into electricity. So, but actually, this shows the volume or the level of energy from the sun that's falling on silicon solar cell. By far, the bulk of it is actually creating heat. So, if you can harness that heat, that's the fuel source, which is PVT. And generally, rule of thumb, if you have a 500-watt solar module, depending on latitudes and inclination, all the system parameters, should be able to extract about 2.5 times, maybe up to 3 times that figure in thermal energy. So about 1,250 watts thermal, maybe even up to 1,500, depending on system parameters. That's an interesting point just on the bottom right there. For every 10 degrees Celsius that you drop the temperature of the solar panel cell, you're lifting electrical efficiency 4%. So if you can drop 40 degrees out of a solar panel from about 80 to 40, which we can do, then you're lifting its electrical efficiency by 16%. And that's significant. There's links in this presentation. You'll see afterwards hyperlinks to this one's to the A2EP. Jared and team, that was an excellent piece of work you did under the ARENA program. But just a quick call out to say that in terms of factory process heat, water source heat pumps mated to a waste fuel source, a free fuel, is now the cheapest form of process heat generation in the world. These numbers are a couple of years old, actually, but it's good data, and the delta is just getting better as the price of gas goes up. Yeah, so I mean, three primary uses of PVT, certainly at a commercial industrial level. Residential, we can have a separate conversation about that. But direct heating for a swimming pool needs a lower temperature output. It's being used quite a lot around the world, in key pockets around the world, as part of the hot water solution in hotels and resorts. And we're talking to you today about what we think is really going to be quite a driver around the world for PVT, and that's absorbing that waste heat and using it as a thermal energy source to improve the efficiency and the COP of heat pumps. And then target applications that we are talking to every day, food and beverage manufacturers seems to be a pretty near universal ability to find solutions that would work either with new build installations or integrating to existing hot water systems. Dairy, choke sheds, hydronic underfloor heating, but industrial laundries, it's a bit of a no-brainer depending on the system configuration and the roof structure and ability to handle some weight. Aquatic centres, we've seen a little bit of that. PVT applied to aquatic centres in Australia really over the last 10 or 12 years to varying degrees of success. There were early movers, but generally that's not necessarily worked so well. But there's a new wave of PVT coming, more reliable and more efficient. Wanted to show you just a very simple generic diagram and how does the PVT integrate with PVT? Well, you can't see it. Effectively, it's totally hidden and hidden behind the solar panel. So on a roof, we'll have to put a label on for you to know that it's there. The plumbing, you will see, although hopefully largely hidden under walkways, just in quite an efficient and elegant way, really, to capture design. Looking at the right-hand side of the screen, that's the important part of this slide, really. PVT systems, they're generally running water. You can run glycol, colder climates, or different, fluid transfer, heat transfer fluids. But if we're talking water, most PVT systems run in sequence, 5 or 6 panels, and they end up needing quite a large or a high-rated pump to go from one, pushing the water all the way through to panel 5 or 6. Panel 1 is hot, but panel 5 and 6 are getting much hotter. So Tom's invented a system that's running in parallel, where we take a pipe along the full length of an array of solar panels, could be 100 panels, 28 or 29 to match inverter strings. And this has a much, much lower pressure. It's a low pressure system, which really means it's much lower maintenance requirements. Less things go wrong. And we have a overall energy efficiency mantra here, really. So this is a much more energy efficient side of the pump, much smaller. So it's and the temperature of across the array is even, which the solar panel people like. Water sourced heat pumps, we think that's going to be an interesting driver for our business, for PVT in the world. Water sourced or hybrid. Number of things really to say there. The Coolsheet system, unless you've got a swimming pool where you're cycling the swimming pool water directly through the Coolsheet, it's rated to run salt water or chlorinated water. But generally, I think you get a more effective and faster ROI by twinning with a water source or a hybrid heat pump. It's a bit of a virtuous loop, because if you take the cold side of the heat pump and you're running that through the back of the solar panels, you're really getting a very nice delta T there and harnessing a lot of thermal energy gain through the panel. And it's effectively working as a preheat to lift the temperature for the inlet temperature to the heat pump. So PVT really works very well as, for the right temperature, for source temperature as an inlet to heat pumps. And that creates a nice loop where you're really capturing a bit of circularity there. We strongly recommend a buffer tank, just so that you're got a stable input into the inlet side of the heat pump, and it's not searching and being inefficient in its energy use. therefore. Yeah, and also because we're storing that at lower temperatures, we're actually capturing a lot more thermal energy at a lower temperature. And then when you step it up to the heat pump for the, up to what you'll be telling us, above 200 degrees now is possible. But we're becoming big fans of water source heat pumps. Europe, the stories are emerging every month really now. That water source, the popularity of water source is really accelerating. It's noise is becoming a bit of a driver at a residential level, but longer life, it's well suited to PV systems, smaller footprint, more efficient. Yeah, so just a quick checklist. This is probably a checklist to look back on or take a screenshot of for the challenges of what we have to look for when integrating PVT with a heat pump system. I mean, it's an obvious thing to say, but we should just say it. At the commercial industrial level, yeah, every system is unique. You've got to start with the load requirements and the plant requirements. But all of these parameters effectively going into good modeling exercise to be dictating optimized sizing of equipment for tanks, buffer tanks, varying different controllers. You can have an incredibly cheap controller if you're lucky for a site, maybe $600 to $1,000. Depends on the complexity of your heat pumps and then your, the complex systems, control systems can be tens of thousands of dollars, of course. So some of these things obvious, but hopefully a useful checklist. Happy to come back and cover some of those in any Q&A. The modeling obviously critical when it's new, if not brand new, certainly new to the market, then that's case studies and modeling critical for engineers and consultants and clients. We've had a number of years now, but 4 years of experience at developing good models. UNSW were excellent in helping us in the early days, creating a plugin for the Coolsheet that then goes into the Transys modeling software. One of your new members, Jared, A2EP, been working with us for a couple of years actually. Real heat pump experts on the modeling side, and shout out to their team. Real deep dive in understanding all the granularity required on making sure you're capturing everything, the energy usage in all the pumps at all levels, the losses in the pipes, all that obvious modeling stuff, but the granularity is giving a lot of confidence. So using Transys is really the best way to model PVT ROI. And then got about a minute to go. Just wanted to highlight the key returns on investment from a PVT system. For sure, it's the subsidy regime that's providing the quickest and largest contribution to ROI. So in addition to the PV getting its STCs or LGCs, you can be attracting the subsidy for thermal for any offsetting. Needs to be done at the moment for our products through the M&V process, larger commercial industrial. We'll get to the standardized kits and STCs, etc., in a year or two. But significant, if you're getting off gas and we can help you do that, sometimes you just need to carry the cost of the system for a year or so, and you've got your money back. So excellent, very, very quick payback if you're able to access M&V. The COP, I'll just run for a few seconds more. Improving and lifting the COP is what this slide's showing you here. And that'll be of interest to people on this webinar. So just obviously a small improvement in that inlet temperature to the heat pump, significantly reducing the energy required to hit the set point. The other points there are obvious ones, and there's some that we can't monetize really yet. Interesting facts, from last year's studies, that if you cool your solar panel by 5 degrees across its life, you extend its life by 50%. You get another 12 years or so out of your solar panel. Can't quite monetize that yet, but it's an interesting one. Yeah, look, I think this is reported where you can find it, but that's what we're finding in modelling. Versus gas, you're saving now between 60 to 80% on your annual operating costs if you're moving off gas to a PVT and heat pump solution. And versus air source, just that energy, the more efficient water source pumps are saving 40 to 50% in energy costs, operating costs. Happy to talk more about that another time. Yeah, so to wind up, we've got an interesting commercial pilot. I think the point to make here is that this, depending, if there's any final design changes on this project, we're hoping this is going to be a CO2 neutral project. So by cooling the modules, we've generated enough energy to offset all the energy being used to run the Coolsheet system. So that's pretty neat from an ESG driver perspective, as well as obviously saving significant amounts of money, over $100,000 a year. So that's the introduction to Coolsheet. Thank you for your time. Some details on screen there for myself, for Tom. Some links on there if that flows through in the recording. And if anybody's interested in thinking we might be able to help you with any low carbon product aspects of your net zero New South Wales grant applications or ITS for ARENA, we'd love to talk to you.
Thanks for that, Doug. And I reflect on, if you go back 10 to 15 years, there was a lot of installation of solar thermal, and a lot of people put that on the roof, and then solar PV got cheaper, and it's almost like, well, I've got solar PV, I can use that for multiple different things, and I'm getting better value out of that. But it looks like, if I've got this limitation on my roof, I can only, say I've only got 400 square meters and I want to get the most out of it, I can. It looks like you're giving them a real option to
yes, correct. Sorry, we forget that, don't we, when you're into it. It's a twofer. It's a classic twofer. If you're short on space, one of the main drivers for Tom, the founder, was exactly that. He was fed up paying a crazy gas bill to heat a swimming pool, and he said there must be some heat in those panels, and that was 5 years ago, and here we are now.
And we definitely see that in swimming pools, a little bit of modelling there, that they often cannot get enough solar PV on their roof, such that you think, well, okay, well, how do we get more out of this? Okay, well, there's that 200% boost there as well. Brendan, where can you see this this sort of thing being implemented there? You there, Brendan?
I think hello.
Yep.
I'm imagining using it in my house. Actually, I got solar panels on my roof, and I just need some hot water when I put my pool in. I can imagine just a very simple. Maybe I had a gas instantaneous heater or a roll for a sports pavilion or something like that, like in a small council application. Perhaps it can just preheat some water for me, so I'm not running those as often as an initial step. Equally, to actually just extend the life of the panels. Perhaps there's another use as well, as a first step to just reduce the reliance on gas consumption, as a bit of a preheat as well, because most of these places have solar panels already. So, yeah, some very interesting, in my mind, like I want it for my house, basically, is how I've walked away going, I want to preheat some water and extend the life of my solar panels. Yeah,
that's going to come. In building our manufacturing business, the commercial industrial is where that immediate scale is, and of course, they need some elapsed time for the residential market to become comfortable with the concept. But yeah, I mean, in a few years' time, you'll have you'll have a combined unit and storage tank on the side with some cool sheets under your panels, and eventually you'll be replacing your instantaneous gas boiler.
I think even Doug, even in larger installations, that's still possible even today. Even if it is only mild preheating, it's still useful. You know what I mean? In some of those larger applications as well. So
so scale matters. In terms of offsetting costs. Early Tom's got a design that's been designed for large scale manufacturers. So when we access volume, we can keep coming down the cost curve to compete, as will happen, of course. But you want a little bit of scale up front that can cover a lot of that installation cost and so on. So retrofit, especially to somebody who's got something on the roof at the moment, it can be done.
I'll get Brendan to go through the questions in a moment. But before I do, Graeme, if I get you to come off mute. Graeme, I know you've done a lot in this space for looking at modelling heat pumps and installations for that and solar PV. These are the two techs coming together. Graeme, your thoughts on how the tech could be implemented?
Well, as an engineer, my mind's immediately going to all the studies we're doing, or should we have done something different, or could we throw another option in the ones that are coming up? So I'm very keen to dig into some of the numbers and look at it. It's certainly for large aquatic pool areas and everything where they don't have much waste heat anyway.
Yep.
It makes an enormous amount of sense because they're short of roof space and they want to do something a bit different. But obviously we play more in the industrial space, and that's going to be really interesting to look at the combinations because we're always looking for waste heat.
Also, of course, those outdoor pools, we've been talking about that in the aquatic centre work we've been doing. Indoor pools, you can recover heat from that exhaust, but outdoor pools, which there's a lot of heated outdoor pools in Australia, there's no waste heat. You're relying on that ambient, and this could extend the life of that performance of that heat pump right through winter much better.
Yeah, and the really nice little benefit of extending the life of the solar panels, that's pretty sweet as well. Lots of
good
benefits, which is great.
Yes. Primary message, I think, is just making that contribution to saving gas, even if it's just offsetting, not replacing. You need a big system offset to replace it. Yeah.
Good. Brenda, we've got a couple of questions come through. Just on mute there, buddy.
On mute. Sorry, I muted myself. Very logical questions, I think, is how does the performance compare to a standard solar thermal system? Just as I guess, as simple as answer as possible.
Yeah, so we're seeking to attack it from a different angle. We're not looking to create, another solar thermal system sitting in your steel tank on your roof for getting to 100, creating steam, again, 120 high pressure system for directly using that water. So we're taking the approach. So PVT can get up to, 50 degrees maybe, but you're not really cooling the module there. And we're taking an approach of sort of capping that a bit lower, call it between 20 and 30 degrees, and capturing a bigger shoulder of thermal energy to step it up through a heat pump. Mm-hmm. So it's not quite like for like. Tom, anything else we wanted to add? But my off-camera help my brain's trust here.
Just the 20% of the energy has already gone to electrical in PVT. So you're only trying to get energy from 80% of the pie.
Yeah, but I guess that's the same for the solar thermal as well. Okay. Well, I'll have a think and see if we can put any more into that one, but it's chasing slightly different things. We're not trying to get the hottest water we can. We're trying to create the biggest energy saving that we can across the piece.
Thank you.
Another question is the average thermal energy output achievable when considering the ratio of thermal kilowatts. Wow, this is per electrical kilowatt peak of a PV panel. I think that's a long-winded question that we can't probably answer here. Perhaps one we can look at in writing if you're sitting there in the background on the chat, Doug. But there's one there about average thermal energy output.
Isn't that just 2.5 to 1? I think that's about 2. So 500 watt panel electrical output, we should be able to get about 1,250 watts thermal, depending where you are, maybe a bit more. So about 2.5 times. And the literature out there is saying up to 3 times. We just like to be conservative. Yeah. So it's then you've then got to harness that, capture it, keep it, and be efficient with it. Waste it. Good question. How does it bond?
Yeah, last one.
Sorry, I didn't. That's critical, and I forgot that. I'm conscious of time. So, a number of people have looked at adhesive. That's not a great solution in our view because thermal cycling, but you're also attaching to a back sheet on the solar panel. You may be attaching to a glass solar panel, but the majority of they have this chemical-based back sheet, and if you have adhesive there, you can create a chemical reaction that might degrade the back of the solar panel. Not a good idea. Tom's come up with a proprietary aluminium fixing solution, so no dissimilar metals, but it's to stand the test of time, right? And we're fitting that here in the factory. We're not screwing into the frame, we're not damaging the frame, but it's holding at big panel 8 points, smaller panel 6 points, just maintaining that through pressure, but not too much pressure. You don't want to put any micro cracks to the solar panel. so that there's no gap, no air gap.
Well, great to learn about that technology, Doug. Many thanks for that. We'll be watching how this progresses, and we're certainly encouraged to see that go into a few more proposals. We're integrated with heat pumps on those, potentially either in the aquatic centres, which is probably a lot of designs going on now, given the funding coming from the government, or future studies under ARENA and things.
Yeah, fantastic. We're a young company, but there's no moving parts inside. All that's on the ground, pumps and all the rest of it, warranty from pump manufacturers. So it's we think we've got an unusual set of circumstances that makes it a pretty safe bet.
Brilliant. And this idea of longevity of the PV panel, that's got to be worth exploring, because there's so much concern over this wall of solar PV waste that's supposed to be coming in 20, 25 years. And if we could head that off and these panels start lasting more than 25, what a great result.
Yeah, no, great. I mean, utility scale solar are now putting 35-year model life in for panels without replacement. But we get inquiries out of the Middle East where they've only lasted 10 years and they're going at half the rated power because they're too hot. Anyway.
Yes, that's good. Thanks very much for that, Doug. There might be a few more questions pop up in the Q&A. If you want to type in some answers there, absolutely, please feel free and go for it. Okay, moving along now, we have Team Beca here. We have Adrian Dickison coming to us from New Zealand. Adrian is the technical fellow and co-founder of the program Maestro for Beca, and he's going to take us through that in just a moment. Joining him is Jack Timmings, also from New Zealand, going to help us out with some projects and what's been happening over there. And then we also have Graeme Harding joining from Beca's office in Melbourne. And for those of you who don't know Graeme, Graeme has a very long history within renewables and sustainable design. And his time in Africa has seen him a little bit ahead of us, because they've had some electricity issues and energy issues over the years, almost necessitating them to be absolutely world-class when it comes to energy. And after doing many different projects within heat pumps and solar, it's going to be fabulous to hear from Graeme as well. But to kick us off, Adrian Dickison from Beca is going to take us through their platform that they have that's going to help optimise the performance of heat pumps. Adrian, over to you.
Thanks, Jared. And just in the same vein as the Australians tend to do now, I'll acknowledge that I'm in Tamaki Makaurau, Auckland, which is where the Ngāti Whātua are the tangata whenua. And without further ado, we'll talk about refrigeration and heat pumps. Okay, we've already seen who we are. And first slide, what is Maestro? Maestro is a machine learning algorithm control system. It has inbuilt digital twins for compressors, and it has a control schema which is always seeking to optimize the performance of a refrigeration system, and largely on the high side. So we're looking at the engine room performance, and that's largely associated with the compression and heat rejection part of the plant. And of course, that has a lead on into heat pumps, which we'll talk about later on. It's system and vendor agnostic, so it can run on top of any system, but really we're focused on ammonia screw compressors for the most part. And also just to comply with companies' IT requirements, we can run this as a totally air-gapped system. We don't have to talk to the outside world. That's one of the questions which comes up quite regularly. Just want to give a quick shout out to Michael Belstead and the AMPC. A lot of the work that you'll see here has been inspired by the work that they've done on energy efficiency. So for those of you who aren't in the meat industry, I would certainly recommend that you get into those documents and have a look at them. They've got some great stuff. It's really clearly communicated with great graphics as well. What is the special thing about Maestro that other places don't reach? Well, it's continuous optimization with varying load and wet bulb every 5 seconds. So what we know is that people are quite used to running refrigeration plants with reset of discharge pressure with respect to wet bulb temperature. But however, we do that for load and temperature because load's varying all the time in a typical process plant. If you're just resetting your wet bulb temperature several times a day, that's not going to cut it in terms of getting the absolute in energy efficiency. And you can see here, and this is sort of a typical plot of where the optimum might lie for a certain set of conditions. But there's clearly a dip which has a significant amount of energy saving associated with it. And just to add some solar flavour, since we're talking to a largely Australian audience, we did have the question, and I think it actually came from Jared a couple of weeks ago. When does Maestro save the most energy? And of course, the answer is at the beginning and ends of the day, because we are basically manipulating the capacity of the system that's available to us when load is not peak load with peak wet bulb. Obviously, if you're in the middle of the day when it's hot and you're processing a lot, you don't have a lot of margin in your system. It will be running close to capacity. So what we kind of do, I describe it as sort of, finding the coins under the cushions on the couch. And that kind of ties in quite nicely with where, you're going to be having higher fossil burn to generate your electricity in your market. And we can see that, our savings are on average in the zone 10 to 15%. Because we have digital compressor twins built into the system, we can look at the performance of the compressors. So we're basically comparing the actual performance with the vendors or the OEM's nominal performance. So you can see here that the expected power is along this barrier between the pink and the green zones. That's the Y equals X line, if you want to call it that. So that would be the expected power for a new compressor at a given condition. And we can see here that the actual compressor in this instance is running typically around about 125 kilowatts higher than the nominal, let's say 375 that you would expect in the brand new condition. And one of the things that we've seen is that people are very interested in doing data-driven maintenance that allows them to justify business cases with paybacks. So you could believe your refrigeration contractor when he says you need to rebuild a compressor. But here we can show, and this is coming out of Michael Belstead's AMPC documents, there is good cases in many instances to replace compressor blocks outright. But simply because with a screw compressor you can't win back the power losses with let's call it a mechanical rebuild. The compressor on the right is part of the same system. It's a VSD compressor, and you can see at the top here we've got a bit of a cap on drawn power, and that's the VSD limiting power at high loads. In this instance, this compressor is actually more worn out at higher loads, and it's actually pulling at a nominal 300 kilowatts. It's actually pulling in reality another 150 kilowatts, and that's why it's maxing out on its motor. So this is a big thing. I think it's one of the unturned stones that's available to us in the refrigeration space. And in that same vein, when we're talking about heat pumps, I would say that we want to bolt a turbo onto a Porsche, not onto a Model T. So if you're going to put a heat pump on a refrigeration plant, make sure first that your refrigeration system is performing nominally and is well maintained. Some of the other characteristics of Maestro, because we're driving discharge pressure set points under our control schema, we get to see many things that you wouldn't normally expect to see just from the raw data in a fridge plant. This is just showing a trend of condenser fan power in 100 kilowatt of refrigeration buckets. And what you can see is that there's a significant change from 2022, which is the green data, to 2023, which is the red data, where we can see at many conditions, we are actually doubling the fan power. And that's telling us the extent of fouling that's actually preventing us from rejecting heat to atmosphere without working the fans harder. And in fact, in like-for-like instances of load and temperature, we're seeing an increase of 18% in the drawn power to reject that same amount of heat, do that same amount of refrigeration. In the same vein, air ingress, although it happens, it's not as insidious as fouling, and it happens episodically. We can also see immediately when air ingress is an issue, and that's really a function of purger performance if you have a purger. And what we know there is that under like-for-like conditions, the power increase under air ingress conditions is typically of order 28%. So, a significant penalty if you allow air ingress to continue for a sustained period. So what are the economic results? So this is from last year's operation of this particular site. The average refrigeration load is about 730 kilowatts. So the drawn power of this plant's around about 250 kilowatts typically. We saved, just with the Maestro schema itself, about $45,000 on 323, so that's about 14% of baseline. However, with the insights that we get, we can see that there's another almost the same amount of saving on the table just through correcting maloperation and fouling. So maloperation, we include running on the wrong compressor, so running on the fixed speed compressor instead of a variable speed compressor at low loads. Too many compressors running air ingress, and fouling. So those two blocks make up those on the table available wins, and that would give us a Maestro target down here, which is something of order almost 30% savings. And then of course we can actually enumerate the compressor losses and show them as a power loss too. And in this system, it turns out to be about 8% of the baseline. So before I was talking about very high compressor power losses, but that's usually at high loads. This load, the plant is relatively lightly loaded, so the compressors don't work too hard, so you don't get the big gas losses from leaky compressors because you've got lower pressure ratios typically. So we can see here that the feasible target with new compressors and good operation is about 35% power savings. So significant improvements available. The next thing we wanted to talk about was some work we've been doing lately in looking at putting a heat pump over the top of a refrigeration plant. So the example I've got here, we've got a classical ammonia refrigeration plant with an evaporative condenser connected to a heat pump. It's connected in a cascade arrangement, not directly, and I would always prefer to separate the heat pump compressor and the ammonia gas from the refrigeration plant for reasons of oil hygiene. And I think many of the OEMs would concur with that. So nominal condensing condition 32 degrees, nominal evaporating condition for the heat pump 30 degrees, so 2 degree delta across that cascade condenser. And in this instance, we're talking about condensing at 70 on the heat pump to make 65 degrees C hot water. And what we've done is we've actually taken real refrigeration plant data running under Maestro, and we put a simulation of a 500 kilowatt heat pump over the top. In this instance, it's a Micom high pressure reciprocating compressor. And so here are the results, and you can see that the results are kind of spiky because in fact, when we're doing the simulation, we're sort of trading off cylinder loading and VSD speed as we manipulate the heat pump to produce the required COP or the required heat. What you can see here, the traces at the top are the COP in orange of the heat pump itself. Now, the reason we're looking at this is simply because we know that anecdotally, people are raising the discharge temperature of their refrigeration systems to make their heat pumps work harder, to improve the COP of the heat pump. Across the bottom of the graph here, we've got saturated discharge temperature for the refrigeration plant. And so the green trace is actually the overall COP. So that is the COP of the refrigeration plus the heat pump duty divided by the total power. And what you can see here is, in fact, to favor the heat pump by raising the saturated discharge temperature of the refrigeration plant, you're killing the overall COP. So you're going backwards. And the reason for that, and you can see here, here's the power trace, the trend of the power trace is going up from around 300 kilowatts, inevitably towards 400 kilowatts. And the reason for that is that as long as your heat pump is smaller than your fridge plant, the fridge plant COP dominates the calculation. So that's what you've got to take in mind. So bearing that in mind, what we did is we said, okay, that was 500 kilowatts of heat pump. What happens if we have different size heat pumps? So we built a family of curves here, but just to show that, and the salient point here is that all of the COP curves, irrespective of heat pump size, are sloping down. So basically, you're never winning by lifting the saturated discharge temperature of your refrigeration system to favor the heat pump. And just here at an optimum, what we call the Maestro optimum, which is what we've determined to be the optimum for this particular system, if we were to lift up from 23.6 degrees saturated to 28.9, we just use more power. And at 29.9, we use 8.5% more power. So the short answer here is don't do that. As long as your heat pump has got enough capacity, it must be slaved to the needs of the refrigeration plant. And that's my bit. Handing over to Jack.
Cool, thanks, Adrian. We've touched upon a couple of really salient topics already. Getting your refrigeration plant tidy, the possibility for solar thermal systems to support high temperature heat pumps. I wanted to take this opportunity to walk you through an example of a heat pump project that I've just been delivering with Adrian's help and others from Beca for a food and beverage client in New Zealand recently. It's a project that we ended up working with the client through the full design process, and the project has recently been commissioned and has been operating very successfully for a number of months. So I thought I would sort of talk a little bit about how that design journey evolved over a couple of steps and some things to look out for in your own projects, with the sort of tagline: the better you understand your system, the better the final design and carbon abatement is going to be. So I'll go to the next slide. Thanks, Adrian. Awesome. So step number one, understand your hot side and your cold side, right? Adrian's point here, I think, is very salient. You need to make sure, I think, before thinking about putting a heat pump on top of an existing refrigeration system, that your existing assets are operating in a way that you would be comfortable with securing for the lifetime of the heat pump. Because putting a heat pump on top of or feeding into a refrigeration network or a hot water network kind of commits you in some ways to operating your assets in that kind of way for the rest of its useful design life. Otherwise, what you'll end up with is a heat pump that's either too big or too small, and capital that could have been deployed more successfully on other parts of the project or in other decarb initiatives across your business line, right? So in this example, on the cold side, when we started working with the client, the duty of the fridge plant that we had initially sort of thought would be a good idea to bang a heat pump on top of turned out to be a lot lower than anticipated due to operational changes that had happened in the plant over the last 2 to 3 years. Not an uncommon thing to see in the food and beverage world, but until we had put some temporary metering on the system, we didn't know that the flow rate, for example, in the cooling water recirculation loop hadn't changed, which meant that we were rejecting water to a cooling tower and bringing it back into the process with a delta T of kind of 1 to 2 degrees instead of 5 to 6, what the system was designed for. So in order to get so before we even thought about doing the heat pump, we spent a bit of time getting that refrigeration system working properly again. On the hot side, we found some other things, right? Some existing control issues in the hot water network for the plant meant that we were needing to artificially increase the designed or the intended hot water supply temperature to account for it getting lower and lower on its way to the users. So that made it more difficult and was going to be an efficiency barrier to installing a high temperature hot water heat pump. So we spent the time working with the operations plant to run some trials and lock in a control schema that enabled it to work with a more suitable hot water temperature. So those two things actually banked us a lot of savings before the project had even started. And I don't think I'd be going out on a limb here to say that similar kinds of opportunities are available to lots of similar operations, even without installing the heat pump. So the next slide, please, Adrian. So a couple of things that kind of surprised us in the data gathering stage for this project, but ultimately the complications that we identified were addressable, and there was still a good business case for the project. But I think in other situations, it's not until you've sort of thought about installing a heat pump that you might actually go out of your way to collect some of this operational info. So once it comes back together, I think one thing I would definitely say is this is a great time to come in and reevaluate your business case. Check your assumptions still stack up. Are you happy with what you found? Might there be some more work to do on your existing system before you move down the pathway to detailed design of the heat pump system as a whole? Cool. Next slide. Thanks, Adrian. So then after we knew we had our data in place and we trusted where it was coming from and we were happy with how the upstream and downstream systems were operating, now we move into cycling through our design options, right? Sizing our heat pump. We tested actually a number of 4 or 5 different heat pump sizes in a model, understanding what kind of waste heat we had available and what kind of heat demands there were on the site before we picked something. And what that kind of modeling exercise showed is that we reached a kind of critical point in which increasing the size of the heat pump, and which is more capital spend, actually didn't deliver us very much additional gas offset or carbon reduction opportunities. So, doing that exercise locked us, identified capacity that we didn't have to install, capital that we didn't have to spend, which was a good result for the project. Then we had a look at thermal storage. Because this was something that was really going to help this project, because a lot of the time the refrigeration plant and the hot water system weren't sort of working eye to eye. They were operating at different times of the day. We had waste heat, but we didn't have a use for it, or we needed hot water, but there was no waste heat to access it. Thermal storage, I think, is a massive enabler for heat pumps to do more with less capacity, because it helps smooth out those operations if the hot and the cold side are out of alignment or one's less continuous than the other. So we ended up installing a low side thermal storage unit to allow us to bank up that sort of low temperature energy over the day, so that we can use it at night when the hot water system was really busy. And then we had to think about other heat sources as well, right? We discovered that this system was one where we could put in as big a heat pump as we wanted. Effectively, there was so much heat demand at that site that we weren't ever going to be able to totally get rid of the gas with just the refrigeration plant. So we had to start thinking about other options. We investigated actually partnering with a number of neighbouring sites going forward when they had asset replacements that were coming up, so accessing waste heat from beyond the site boundaries. None of those opportunities lined up during the stage 1 project implementation scope. But, we've talked to them about a couple of asset refresh opportunities in the next 5 years, which look really promising. But we did end up installing some solar thermal generation to work kind of in tandem with our refrigeration plant's heat rejection to increase the role that our heat pump could play. Next slide, please. So designing a heat pump together, from that point of view, is a lot like putting together a puzzle, And I think the most important thing to do is make sure you know the size and the shape of all of the puzzles you've got before you start trying to put them together. And also have an awareness of how new pieces might be able that you could bring into the puzzle, like other heat sources, thermal storage, optimizing your plant, could change the final picture that you build for the heat pump system itself. Next slide, please. So yeah, you'll see actually Adrian in one of the orange vests in this picture, but the project has been running for a couple of months now. I've put in a couple of choice photos of the heat pump skid provided by JCI. I think I see Ricky from JCI on the call today. We had some really great vendors come in and support us with the final design and delivery of this project. Here's a little picture of some of the solar thermal panels we installed, evacuated tube, evaporator panel type arrangement. And you can see there's the heat pump, and right next to it's the big thermal storage tank we put in. At the moment, the system's up and running. We've gotten rid of about 80+% of the existing or the previous gas utilization at the site, and we've improved a bunch of operability and reliability issues that the operations team have been working with. So, really cool story. Hopefully some of the stuff I've talked about today has been helpful for people on this call who might be thinking about their own heat pump journey. But thanks for the opportunity to speak, and I'll hand over to my colleague, Graeme.
Hi, thank you. We are running short on time, so I'm going to go quickly through two case studies, building on what Jack and Adrian have been doing. So the first was a 2011 ammonia heat pump project. And at that stage, there certainly weren't package chillers available. I didn't have Adrian sitting around to tell me not to install it directly on the high side. So that's exactly what we did. And because I think we were only producing sort of 60-degree water, it has run quite successfully since then. So there's a lot to take in on this diagram. Firstly, I'll just talk you through the water circuit. That we installed a new condensing heat exchanger in parallel to the evaporative condensers. And so we preheated the water to about 30 degrees. And then we then took that water through the heat pump. And then the heat pump only had to boost it from 30 to 60 degrees. And that condensing heat exchanger is a lot cheaper than a heat pump. So it made a lot of sense in terms of the overall performance. And then on the ammonia side, as I said, it was installed on the high side, basically taking the discharge from the compressors and boosting it up to sort of 60 degrees to condense at 60 degrees, produce hot water. And then that ammonia went into the common liquid receiver. So moving forward to the next slide, thank you. Here's some pictures. That's the condensing heat exchanger, effectively boosting the condensing capacity. Next slide. This is the heat pump. It was a reciprocating heat pump. I regret not being able to find any photographs from inside, but we got great performance out of it. The overall hot water COP was over 9 because of the preheating, although the COP on the heat pump was probably 6 or 7. And we had great data, and it's been running for many years since. If we can go to the next slide, please. As I said, we were obviously recording all the ins and outs and temperatures and power, so it was easy to calculate that. We've got a great overall COP. In the project, because we were competing with an electric boiler, we had a great payback, and it was about a 2.5-year payback at the time. And for the client, this was a chicken processing facility producing patties for Kentucky Fried Chicken. And the only thing that really we had to be aware of that caught us a little bit on that job was we needed at least 2 high-side compressors to run all the time to provide enough ammonia. And we did notice that when the heat pumps were running in the evening, we dropped the discharge pressure, and so the hot gas defrost didn't work so well. And so we had to move the hot gas defrost time, and then everyone was happy after that, and it's performed very well. This is a more recent study we just did, and this project is currently being installed in Queensland. And there we were also very keen to install heat pumps, but we needed a much higher temperature, and we obviously needed a lot of waste heat. So we modeled it throughout the entire year, and the red line is really the amount of waste heat that we required. And unfortunately, we didn't have enough. The bars below it are the sum of all the waste heats, available waste heat that we were trying to grab from all over the site. We didn't have this solar panel heating idea, although we did put solar on the roof. And there just wasn't enough waste heat, and combined with the fact that we really needed over 100 degrees, large amounts of over 100-degree hot water. And so we didn't go for a heat pump, and we did an overall, next slide please, life cycle assessment of all the options. We compared heat pumps, gas, electric, and for this particular case, a biomass hot water boiler was the solution that ended up being installed with an ORC, and that's currently being installed at the moment in Queensland. And that's me rushing through just the last few slides. Thank you very much for your attention.
Graeme, thanks so much for speeding through to get us a little bit back on schedule. I haven't seen any fresh questions come through. Let me just throw to Brendan. Any questions or observations there, Brendan?
I'm still digesting how much information we were just given in a short space of time. But I feel like I learned a lot in a short space of time. So I think the key takeaway for me was, and I come from a trade background, so making sure things are running properly should always be done, regardless of any upgrade you're doing. I think that's my key takeaway is you don't want to end up with something too small or too big that you're stuck with forever. So the importance of maintenance is always reigns supreme, I think. So.
Brilliant. And we've been asking that question over the last few years, actually, that Adrian's now answered about should you let that condensing temperature for the chiller the refrigeration plant start going up to try and help the heat pump. And looks like we got that answer, that question answered today. Thank you, Adrian. And that looks like, yep, no. In that scenario that you presented with every time the heat pump was smaller than the refrigeration plant, no, still optimised for optimal suction pressure and what have you. So maintain that floating pressure control for sure. So thank you, Adrian. And lots of other takeaways there. Yeah, my brain is full of probably. I think I might need to watch the recording. Usually I don't need to watch the recording, but I think I'm going to need to watch the recording today. There's a lot coming at us there. So thank you so much there for our presenters. We'll try and wrap it up here now. So Doug, thank you so much for that presentation. Graeme, Adrian and Jack, thanks for joining us today. And in terms of just a quick wrap up, I'll let you know what's happening going forward over the next couple of webinars here. So this is our webinar month. That's 2 out of 4 done. We've still got a couple to go. Next week, we are going to go through a really high-speed run of different projects. You've seen last week, there's a lot of things happening in high temperatures. This week, there's a lot of technology and improvements on how you operate them. Next week, we're just going to hit you with lots of examples of where heat pumps are being used across commercial and industrial. After that, we've got on the 27th a site tour. Really keen for people up in Brisbane to join us there. Let's go check out a heat pump and aquatic centre. What's happening with Griffith University and the amazing work they're doing on biogas there. Biogas has to be a part of the renewable heating solution. And we're going to go see one of these gasification plants that are producing that biochar at the Longhorn wastewater treatment plant. After that, the Thursday after that, the day after, we're going to go through geothermal and ground source heat pumps. We've got a stellar lineup there for you there. I'm going to take a deep dive into what's happening in that technology and how that's moving forward. And then also looking forward, we've got next, just coming up actually tomorrow, the A2EP member collaboration pod, where we're going to go through the different grants that are available and really try and get that confidence up and understanding of how to win these arena grants and this New South Wales manufacturing initiative grants as well. So yeah, a nice full schedule and hope you can join us. All that's left to say, if you want some more A2EP, follow us on LinkedIn. Always lots of stories coming out there and you'll get plenty of value. Otherwise, many thanks for joining us today. We look forward to you joining us at our next webinar. All the best. Bye-bye.